Hello, and welcome to Part 2 of Learn C for Cybersecurity. In Part 1, I explained how to use Vim, GCC, and Bash to edit, compile, and execute C programs for the first time. If you have not already done Part 1, I strongly suggest you pause this video and see Part 1 first. Once again, I will say this. You are expected to already know Java, C++, Golang, or another C-based language, preferably C++. After the end of this video, I strongly recommend you visit the link in the video description for exercises and the solutions manual. With saying, I'll begin the next topic. Printf escape characters. In Part 1, I explained how you print basic data types using the printf function. Here, I will explain how to print escape characters. These are non-visible characters that format the spacing of a printed line. Here's a table of the escape characters. Give you a good look. The ones you really need to care about are the new line character, which you should have already used if you did Part 1, carriage return, tabs, backslash, single quote, double quote, question mark, and hexadecimal value. This is repeated here in this line for your reference. You can more easily ignore the rest. Throughout my coding in C, those are the escape characters I dealt with firsthand when reading or writing code. Below is sample code demonstrating how they are used. Let's compare the code versus what the terminal output is. When we look at this, we see that the tab character aligns the numbers 1, 2, and 3 automatically without spaces. Tab character is often used to assemble tables in the console for this reason. The carriage return needs more explanation. What happened was the computer first printed 0, deleted it, printed 1, deleted that, and this process repeated until 9 was printed. Let me go ahead and simulate that in the terminal on purpose. So once again, 0 was first printed. It was later deleted. Then 1 was printed. It was later deleted. Then 2 was printed. It was later deleted. And this cycle repeated until 9 was finally printed. The cat command does not automatically do what carriage return does. I just used it to simulate what the carriage return does. That's all. Over here, we see backslashes are printed. To do that, we had to format double backslashes for each backslash we wanted printed. This is done to help the computer tell the difference between specifying a escape character versus actually printing the backslash character in itself. Here, in line 6, we see the quote there here. To do this, we needed to use the backslash apostrophe character to print the apostrophe seen here. And in line 7, we see the question mark symbol, or they here with a question mark. To do that, we had to use the backslash question mark character. Finally, we have a line in line 8 that says the quote from the film was "see you later" in double quotes, literally. This time explicitly seen. To do that, we needed to do the backslash quote, both for the opening and closing quote, double quote, followed by the backslash new line for new line character. You can read more about my explanations below. I'll give you a few more seconds to compare what was written in printf versus what was printed for the next 5 seconds. All right, let's move on. Let's move on to basic arithmetic operators. In the last tutorial, I explained the primitive data types in the C language. In this tutorial, I will now explain how to do arithmetic using basic operators. So the following code demonstrates simple operators used to do calculations amongst 2 or more numerical primitive data types in C. We already talked about what integer-based primitive data types exist in C in part 1. If you are confused about what these mean, go to part 1 now. You need it to understand this code. Notice the familiar operators that you used in elementary school, with one exception, this strange-looking double % symbol. The double % symbol, when specified in the first argument to printf, specifies for the % character to be displayed. I'll talk more about what this % character, how this % character symbolizes an actual arithmetic operator in C-based languages later. For now, I'll just give you a few more seconds to compare the output, compare what's in printf versus the output. Immediately, we notice something. The first 3, addition, subtraction, multiplication, the results are exactly what we expect them to be in elementary school arithmetic. But as for division and percentage, that's not percentage, that's something else. It is something different from what we are used to. When first is assigned 1, whenever you see a single equal sign, always read assigned. When first is assigned 1, and second is assigned 2, we would normally expect the answer to be 0.5. But notice we don't get that. Instead, we end up with 0. The division operator you see here is not the grade school division you are used to. Java and C++ coders should be familiar with what the division operator truly does. It's called truncated division. In truncated division, the result is rounded to the integer closest to 0. This explains why we see the result in line 5. That says line 6, I'll fix it. It actually means it's supposed to be line 5, my bad. Although 1/2 equals 0.5, the final result is actually 0. Because, once again, the truncated division rounds to the integer closest to 0. And the integer closest to 0, in the case of 0.5, is 0, not -1. This happens due to the nature of binary division. How that exactly works is beyond the scope of this tutorial. It does not matter how close the decimal is to the next integer. As an extreme example, consider the following code snippet. So, typically, we would expect such a division, int numerator divided by int denominator, to give something like 0.99999 and so on. Instead, we wind up with 0 because, once again, the integer closest to 0, in the case of this division, is going to be 0, not 1. Having explained truncated division, I now want to turn my attention to the modulus operator. That is the true name of the strange-looking % symbol operator that you noticed earlier. Up here. This means whenever you see this, say modulus. Do not say %. Modulus. That's its true name. If you had an introductory programming class, you were told that this calculates the remainder. I'm sorry to tell you this, but that is a terrible definition, and that's because the modulus operator even works on negative integers. A more accurate definition is the following. However, I'm going to admit it, even this mathematical formula does not always correctly give what the modulus operator in C really does. I actually decided to leave it as an exercise for you to figure out code that does the equivalent of what modulus does in terms of other arithmetic operators to test if you really understand how it works. For now, I will explain this math formula. So this strange-looking square bracket symbol is the floor function in math. Unlike truncated division, floor division rounds a decimal to the next integer closest to negative infinity, whereas truncated division rounds a decimal to the next integer closest to 0. Truncated division is what Java and C++ coders are used to, and it is what modulus is based on. Hint for the exercise. The modulus operator is based on truncated division. That's my hint for the exercise on implementing the modulus operator in the future exercise for this tutorial. You are probably not familiar with floor division. Take the time to really understand the difference now. Go ahead and pause this video. Think about what I said. Give you 3 seconds. Let's move on. The above formula for modulus will work even when a is a negative integer in this formula. Below are sample calculations applying to the mod operation. You should pause this video right now and read these carefully. Go ahead. I'll give 3 seconds for you to pause the video and take a look. One thing you want to notice is that this formula always ensures the final result is a positive number. That's what you see here. It's not ever negative. The modulus operator that you see in C and C++ will actually give a negative number because, again, the modulus operator in C and C++ is based on truncated division, not floor division. I'm just saying that out loud a second time. That will help you complete the exercise in the future exercises section for this tutorial. I will give the hint once again. You may be wondering why this strange operator exists in C and C++. Do not neglect it. Do not neglect to understand the modulus operator. It will be really helpful to know how to use it wisely throughout your programming career. Once again, there will be an exercise that really tests if you understand what was just taught. Pay attention to what I said about the hint earlier. I'm not going to repeat it. So here's sample code that displays the result of applying the modulus operator. I intentionally decided to make a negative on purpose to demonstrate there is a difference between what you would expect from the math formula here and what you're going to see here. Typically, we would expect negative 6 modulus 5 to give 4 modulus 5. Instead, we end up with negative 1 modulus 5, which is equivalent to 4 modulus 5. I will repeat this again for you. Negative 1 modulus 5, the result we see here, is equivalent to 4 modulus 5. The answer 4 modulus 5 is the answer we would get if we used the floor division formula here. Meanwhile, the formula based on truncated division, an exercise to leave to you in the exercises section, will give an equivalent negative answer, negative 1 mod 5. Go ahead and read this paragraph as a reference to what I just said. Take the time to understand it. I encourage you to pause this video and change the values of a and b yourself. What happens when b is negative? Compared to the result of the math formula I gave, the thing is, in the floor division formula that you see in math, n is supposed to be greater than 0. However, ironically, the modulus operator in C and C++ allows b to be negative. And once again, the modulus operator is based on truncated division. I'm giving the hint once again. So go ahead and compare the results. Go ahead and download this code. Compile it the way I showed here. Tweak these values. Change them. Modify them. And remove all doubts and concerns and confusions you have about what the modulus operator does now. You're going to need it for a future exercise. Let's move on. The typecast operator. So, about the typecast operator, it converts a value to the data type of the variable it is assigned to. As a rule of thumb, you should only typecast a value to a data type of the same class of variable, and that at least has enough memory to store the data. Here are some rules of thumb for you to remember. Do not typecast a floating point value to an int. Do not typecast a value to a variable of a data type that has less memory than required. Do not typecast a signed integer value to an unsigned integer variable. In general, you should be cautious about typecasting an unsigned integer variable to a signed integer value. And the reason is, you could store more positive integers in an unsigned integer variable than you can in a signed integer one. So watch out. So here's below code demonstrating how that works. Notice that we specify the exact primitive data, the exact data type we want in parentheses. So in parentheses in the is target data type of typecasting. That's how it's done. Take a moment to read the first part of the code here. Let me explain this line. It says safe, meaning it's safe to do this. So what we're doing is we are typecasting C, which is of data type unsigned car, as an unsigned integer A. And the reason why this is safe is, number one, unsigned car only takes up 1 byte of memory, whereas an unsigned integer takes up 4 bytes of memory. So typecasting C to A, there's enough memory to do that. 2, both are unsigned integer-based data types, A and C, so it's totally fine to do. Let's go. Let me give you one more minute to look at this code. Go ahead and download the code and try to tweak with the values and see what happens. See if you find any weird behavior. Get used to seeing that so you can predict it later in future exercises. Let's move on. So what's this strange question mark symbol here for 255? Data type unsigned car, variable D. What happened is, so this is printed here. What happened was we had an unsafe conversion from signed car B, from, not signed car, my bad, int B, to variable D, which is an unsigned car. So there isn't even enough memory to do this properly in the first place. And that's the biggest problem with it. It is impossible for us to tell exactly what was printed thanks to the question mark. But the point is, expect data to be lost when you do something like this. If there's not enough memory to store the original right-hand side value, to the left-hand side, you're going to end up with potential memory loss. The most significant bits after the least significant byte might have been lost. No guarantee that everything was kept intact. I messed up. What I meant to say was this symbol over here. That symbol was actually meant my bad. So what actually happened was for this line, B 255 question mark symbol. What happened was we converted unsigned car D, which is 255, to an INT. Technically, you can actually do that because 255 fits in a 4-byte data type. That and 255 fits in a signed integer data type, so that's safe. Just be aware that it's easy to mess up the differences between the signedness. Remember, it's easy and tempting to store an overly sized integer as an unsigned integer in a signed integer data type that stores less positive integers. I wouldn't do this anyway, even though it's technically safe here, because it's a bad habit to try this. Generally, you want to make sure that the two integers from conversion to target data type have the exact same amount of memory and have the same signedness if you're dealing with integers. What I was talking about earlier, that's with line 6. So here we see B being printed just fine, and B is a int. Meanwhile, D is an unsigned car variable. So what happens is -1 was assigned to D. The problem with that is when you, in order to represent -1 in binary form, all of the binary digits in the variable have to be set to 1. So remember how an int is stored. It's a sequence of 32 bits. Imagine all the bits being set to 1. The truth is, there are more bits than unsigned car has space to carry. So that's unsafe. Technically, this should be the EOF byte. But still, don't do something like that. Finally, let's look at the short decimal. This one's the worst one. So we typecast a large decimal, which is overly too large, into a short decimal. Notice that large decimal is of type double, and notice that short decimal is of type float. What happened was, there was data loss. Look at this. That's infinity. There's no way that should be infinity. It should be 1.7 E308 instead. But of course, since float doesn't have enough memory to store this very big integer in binary form, you get this, infinity. The compiler thinks it's too large to represent numerically when it's not. Finally, I would like to give a comment that's not necessarily related to integer conversions, but it's a problem with printing decimals. Notice that the final integer printed, final decimal printed for large decimal, which is 1.7 times 10 to the power of 308, isn't precise here. There is some loss of precision. 1.69999 and yada yada times 10 to the power of 308. That's what really happened. The thing about decimals is, it's what I said in part 1. It is very easy to lose precision when doing floating point calculations with either double or float. That's why security critical applications often use integer-based data types, unsigned integer-based data types, to avoid data loss. They avoid using floating point data types on purpose. So to be honest, all the conversions, even the unsafe ones, were fine in the above example with the exception of the last one. The last one was a disaster. All of the others, luckily, more or less worked, but you shouldn't do them even though they technically worked in this case. It's not safe to do. Let's move on. Let's talk about PEMDAS. In grade school, you learned about order of operations for arithmetic. In order of operations, the following are evaluated in descending order of precedence. Parentheses, exponents, multiplication and division with equal precedence, addition and subtraction with equal precedence. The C programming language supports PEMDAS expressions for integer values, floating point values, and variables of such values. So here's an example. I decided to stick with integers for the sake of accuracy and precision in the final calculation. For expression, the result we get is exactly what we expect it to be in grade school math. Same thing with expression 2. Give you a minute, give you 30 seconds to see that yourself. Do the math yourself and verify that. To be honest, PEMDAS should be easy for you to understand if you already know and are trained in Algebra 1 and beyond. So I'll just move on from there. Let's move on to Boolean logic. This is how machines make yes or no decisions at a basic level. Coders experienced with Boolean logic in Java or C++, or another C-based language, should be familiar with the phrase Boolean logic. If you didn't know what they are, here are the Boolean logic operators. Boolean and, logical or, logical not. Look at these truth tables, and pay attention to how these operators affect the final decision, whether the statement is true or false, whether the expression is true or false. Give you about a minute to take a good look. Let's move on. I want to take a moment to talk about the logical equals operator. logical equality operator tests if two values are equivalent. So when A is assigned about the numbers, I'm sorry, I didn't explain this earlier. In Java and C++, it's normal to represent Booleans as true or false. In the C language, and before macros like true and false were invented, coders actually expressed true in logical operations as the number 1. They expressed false as the number 0, and that's why you see this here. Taking a look at this table, when 0 or false is A and B is 0 or false, and we compare their logical equality, we of course get true 1 or true because they're both equal to each other. This explains why this outputs 1 for A is logically equal to B. And this also explains why these two output to 0 for logical equality. They're not the same as each other. If you're new to C and you're too used to seeing true and false, you need to wire your brain to get used to 0 representing false and 1 representing true. Get used to it. It's something that C coders do a lot because, again, there's no native support for true or false. You'll see a lot of legacy code that does this throughout your career, so get used to it. Now, let's take a look at the following code to understand how to use the Boolean logic operators. So here I just assign A is assigned 0 and B is assigned 1. Let me go ahead and say something. For beginning programmers, it is way too easy to get confused with the difference between the assignment operator, this is the assignment operator I'm highlighting here, and the logical equality operator. Whenever you see this, know that it means we are assigning a right-hand side value to a left-hand side variable. When you see this, know that we are comparing the value of a right-hand side value to a left-hand side value, and we're checking if they have the exact same value. If so, 1 is returned. If not, 0 is returned. Based on the truth table you saw previously, the following results should not surprise you. Since A is not the same value as B, we get 0. Since A is 0, even though B isn't, we still get 0. Since at least B is 1, we get 1. Since A is 0, we get 1 when we apply the logical not operator. Since B is assigned 1, we get 0 when applying the logical not operator. Boolean logic is something that can be confusing to newcomers. I encourage you to download this code. You can download it by clicking on this, Open Raw, or clicking on the download button, but I like clicking raw and copying and pasting. And compile the code and play around with the values A and B and see the difference in the output versus what you see here. That's going to help you get an idea of what these logical operators do. You need to know this for the exercises, so get on it. You absolutely must know how these Boolean operators work like the back of your hand. Do not escape this and pretend you don't need to care. Moving on to binary and hexadecimal encoding. So far, when we assign an integer to a variable, let me show you an example of that, such as here. Or here, we assign it in base 10 form. Base 10 form. The thing is, there are other ways to represent integer values in C code. We can also assign values in binary and hexadecimal form. What is binary? Well, binary system is a way to represent numbers using base 2 digits. In order to know what kind of digits exist in a base numeral system, you should pay attention to the digits right before the base numbering system. So since we're talking about base 2, 0 and 1 are valid digits in a base 2 numerical system. Humans prefer the base 10 system, which allows 0 through 9, the digits. Here in this diagram, it shows how to actually convert a base 2 number to a decimal number. What happens is, we first take a look at the binary digits, and of these binary digits, you can write down the powers of 2 associated with them. So starting from index 0, we go all the way up to 7. 1 times 2 to the power of 0. That's a start. Moving on to here, 1 times 2 to the power of 3. That's 8. Moving on to here, 1 times 2 to the power of 4. My bad, I messed up. 1 times 2 to the power of 4, and so on. Adding up all these, adding up the products of all of these to get the final base 10 answer. 57 base 10 is equivalent to this base 2 binary number. Give you a few seconds to take a look at this diagram, get a feel for the conversion from binary to decimal. You need to know how to do this. Give you 3 more seconds. Below is an example of converting a base 10 number to binary form. What we do is we repeatedly divide the current most quotient, which starts with a number we are dividing by, 100 in this case, and repeatedly divide the quotient by 2, keeping track of the remainders until we hit a quotient of 0. 1 divided by 2 is basically 0. Truncated division form, that is. So we then juxtapose the remainders from bottom to top. There's supposed to be an extra 1 here. That never is shown here. Sorry about that. This code demonstrates that the explanation here is correct. It actually tests for the equality of the two numbers, and it also shows how to assign a number in base 2 form. Unsigned car A is assigned 57 in base 10 form, meanwhile unsigned car B is assigned 57 in base 2 form. And we can see clearly that they're the same number. Same logic for C and for the comparison between C and D. Likewise, hexadecimal encoding follows a similar logic. Unlike base 2 encoding, since it's a base 16 system, we have the digits 0 through 15. Now that's cumbersome to express. So all digits with more than one digit in a base 16 system are represented by a letter. Notice that starting from number 10, we represent these numbers as letters instead of the actual number, and that's just an easier way of expressing it. Compare the base 10 number to its base 16 form to its base 2 form now. I encourage you to pause this video now and take a moment to memorize the above table. You are going to need it for the rest of your life if you're coding in C. Giving you 3 more seconds. Note that any 4 binary digits map to a hexadecimal digit. It is also possible to print numbers in hexadecimal form using Printf. The following code demonstrates this. Notice that we actually specify the base 10 form of the number, yet in the first argument of Printf, we use this %2x, meaning we want to print 2 hexadecimal digits representing the corresponding argument. And we get the following terminal output. And the reason why there's only one digit for each is because that's the way base 16 works. Whenever you want to express hexadecimal coding, however, you might want to try you need to specify calculate how many hexadecimal digits it will take to represent the number. Whatever amount of digits, hexadecimal digits that is here, replace 2 with the number of hexadecimal digits required. Once again, notice that instead of saying 10, 11, 12, 13, 14, 15, it's A, B, C, D, E, F, just as we saw here. Below is sample code that does the reverse. It specifies the numbers in hexadecimal form. Notice the A, B, C, D, E, F, but we ask it to print the unsigned integer form of the number. And we get the inverse. This time, 10, 11, 12, 13, 14, 15 show up, because we're asking to print the unsigned integer. of form of the number in base 10. %u, %d, all of these specify base 10. %x specifies base 16. Keep that in mind. We can also print any integer in hexadecimal form in C, as I said earlier. This time, we assign integers in hexadecimal form and print them exactly in hexadecimal form. This time, we specify with the exact number of hexadecimal digits required. First, we specify 0 to tell Printf to explicitly print leading zeros that are insignificant. That's done here and here. We then tell Printf exactly how many hexadecimal digits we want to print, which is 2 in this case for C, 8 in the case of integer, and 16 in the case of ULL, because it's a huge number. And we see the corresponding hexadecimal number printed as so. I prepended the 0x string on purpose for ease of reading. To convert hexadecimal numbers to base 10, you should see the following diagram. Note that the conversion of hexadecimal numbers to base 10 is similar to the process of converting binary numbers to base 10. Give you about 3 seconds to verify that yourself. Below is the case of converting a decimal number to a hexadecimal number. Notice we have to repeatedly divide the number we're asking for base 16 form in by 16 until we hit 0 as the final quotient. We then juxtapose the remainders from bottom to top to get the final answer, 23A4 base 16. At long last, I want to discuss bitwise operators today. The bitwise operators apply the Boolean logic operations to each individual bit in the operands of the expression. Take a moment and think about what I said. Logical operators, they are usually used as if each operand in the logical comparison is either a 0 or a 1. In bitwise operations, each and every individual bit is considered, and the operator considers each and every... And the bitwise operator considers each and every individual corresponding bit between the operands. Keep that in mind. Here is a table demonstrating what each bitwise operator does based on the inputs for A and B. So this is bitwise OR. If at least one of these is 1, this evaluates to 1, just like the logical OR. This is bitwise AND. If both of these are if at least one of these is 0, it evaluates to 0. What's this? This caret sign thing. This does not mean A to the power of B, I promise. It means a XOR, exclusive OR B. Say it out loud. What this means is it tests if the bits are differ from each other. If so, you're going to wind up with 1, as you do here and here. If they're the same, you get 0. Finally, we have the bitwise negation of A, which is sort of like the logical NOT operator. In which case, it gives the opposite bit that A is assigned. Hence why you see these results. The following is code that demonstrates how the bitwise operators works. I chose these patterns on purpose for ease of comparison. And the actual result of the bitwise operation is I explicitly defined it in base 2 for ease of comparison. Here, I actually extracted the least significant 8 bits on purpose because those are all that matter. Keep in mind I stored 8 bits in unsigned car, and I extracted it this way on purpose to maintain information and preventing extra information from being represented because I'm printing as a unsigned integer here. for the sake of demonstration. So I had to extract the least 8 significant bits, the last 8 significant bits in the bit stream on purpose to make sure that printf doesn't print extra digits. That could lead to imprecision problems, by the way. So yes, get used to extracting digits, the exact digits you want in binary form. It's a useful skill. I encourage you to pause this video right now. Download this code, play around with A and B a lot, and see how it affects these outputs. The only way to learn how to code is to read code, play around with it, tweak it, experiment with it, not by listening to a person lecture in a lecture hall. That's why this tutorial actually has exercises and a solutions manual to check your work. Giving you 3 more seconds to take a good look at this. The last operator I want to talk about today is the bitwise shift operator. The following program demonstrates the bitwise shift operators. There are 2 of them: bitwise shift left, bitwise shift right. You could ignore what this does. I don't expect you to truly understand it. It uses a recursive formula for those of you who experience Java and C++ coders, but I'm not going to expect you to understand what it does. Just know it works. I used the dead hexadecimal number to help you understand what the results. Dead beef, 0x dead beef, is a valid hexadecimal number. It's fun to say, and I think it's a very good, easy to understand example here. When you look at the examples, notice what happens when I shift by 4 binary digits, bitwise shift right. What this does is it technically gets rid of the last hexadecimal digit, which represents 4 bits. Remember what I said earlier. All the way up here, that's that's D, my bad, 1101. That's gone. Because that's 4 binary digits, shift to the right, so that's erased. All the way down here. When you do bitwise shift right 8, these 2 are gone. When I do it by 12, the last 3 hexadecimal digits are gone. When I do it by 12, all of them are gone. Oops, that's wrong. Just 3 base 16, my bad. That's a mistake in the code, sorry. When you see this, I want you to think of 16, my bad. So the same logic applies for bitwise shift left. When you shift left by 4 binary digits, we have an extra hexadecimal digit entirely. And to make the matter more clear, there are 4 extra zeros, 4 extra trailing zeros. When we bitwise shift right 8, we now have 8 trailing zeros. When we bitwise shift left 12, we have 12 binary trailing zeros. When we bitwise shift left 16, we have 16 trailing zeros. Seriously, if you haven't already, pause this video now. Download this code that you see here. You can do that by either clicking on raw and copy and pasting, or by downloading directly. Play around with the code and take the time to understand it, because the exercises are going to grill you on whether or not you really get it. If you enjoyed this video, please like, subscribe, click on bell notifications, and expect more content in the future. I enjoy making this for a young cybersecurity professional. Thank you so much for your time. Peace.